In this video, I will show you how to define your own CNC winding system in TaniqWind Pro. During the video, I will be demonstrating the process of defining your CNC system so that it can be used in your production process. If you want to know more about setting up the CNC production process, this is discussed into more depth in the CNC production video. I will start by opening the machine library. In here, we can see all the defined CNC and robotic machines. In this video, I will demonstrate the definition process by recreating the shown 5-axis CNC machine with the roller material payout. The CNC machine definition consists out of 4 main components which need to be defined. These are the available axes with the respective parameters, the material payout, the post-processor, and the zero position of the machine with respect to the origin of the coordinate system. The origin of the coordinate system could be set at any point along the mandrel axis, but in TaniqWind Pro it is easiest to set the origin of the coordinate system at the start flange of the mandrel axis. This location is shown in the schematic figure. In the plot we can see the 3 linear axes, with the blue line representing the Z or the carriage axis, the red line representing the X or cross carriage axis, and the green line representing the Y or vertical axis. We can see the origin of the coordinate system position, which is the separated triad with the mandrel axis from its Z axis. The machine is displayed in its zero position, which we will discuss later. If we zoom into the material payout point, we can see the TCP or the tool center point triad. This is the calibration point for defining the location of the tool. Here we can also see a visualization of the rotational twist axis. Now I will demonstrate how we can recreate this 5-axis CNC machine. We start by pressing the Add CNC button to create a new CNC machine definition. In the machine definition panel we can see 4 tabs: General, Axis, Tool, and Post-Processor tab. In each of these 4 tabs, one of the 4 main components can be set. We will start in the General tab, where we can start by setting the general machine information like the name and possibly a manufacturer's ID. In the General tab, we can also set the zero position. This is the machine's reference position measured with respect to the origin of the coordinate system. In TaniqWind Pro, this reference position is the location of the machine's tool center point, and the position of this tool center point should be measured by jogging the machine axis to the following configuration. 1. All of the linear axes are jogged to their zero axis position, and 2. All rotational axes are jogged to have zero orientation with respect to the origin of the coordinate system. With the machine in this position, the X, Y, and Z coordinates of the tool center point with respect to the origin of the coordinate system should be measured and filled in. The location of the tool center point used for the measurements should be consistent with the tool center point location in the payout definition in the Tool tab. In the Machine Parameters section, we can define custom parameters applicable to the whole machine. For this demonstration, I will set a tape tension parameter with a default value of 30, which is non-constant. The use and integration of the machine parameters are explained into more depth in the Productions Parameter video. Now we can move to the Axis tab. In this tab we can define the axis our machine has. Every CNC machine needs to have the mandrel and the Z or carriage axis defined. These cannot be turned off. Aside from these 2 mandatory axes, there is an option to define 4 more axes. 2 linear axes in the X or cross carriage axis and the Y or vertical axis, and 2 rotational axes in the twist and yaw axis. The twist axis is the rotational axis aligned with the X or cross carriage axis, while the yaw axis is the rotational axis aligned with the Y or vertical axis. For this machine, we also select the Y or vertical axis and the twist axis. For every axis we are using on our machine, we must fill in the minimum and maximum position of the axis to be reached when jogging. The value of the minimum position should be non-positive, and for the maximum position the value should be non-negative. The resolution defines the axis resolution and direction with respect to the origin of the coordinate system. The absolute value of the input defines the conversion rate between displacement and the axis increment. The sign of the value defines the axis jogging direction with respect to the aligning origin of the coordinate system axis. For the velocity and acceleration, the nominal velocity and acceleration of the axis should be given as a positive value. The twist and yaw axis also need to have the eccentricity defined. The eccentricity defines the length of the rotational arm of the axis. The sign of the value determines the direction of the rotational arm in the zero position, whether it is in the same direction as the corresponding origin of the coordinate system axis or in the opposite direction. Depending on the number of axes, certain production settings might be disabled since they cannot be used by the machine. With all of the axes defined, we can move to the Tool tab. In this tab, we can start by setting the material outlet type. For this machine, I will set the material outlet type to be a roller, for which we'll have to define both the width and the radius. For the material output position, we can specify the angular position around the rotational axis of the geometry from which the material should be output. By changing the output angle, the material output visualization changes accordingly. With the Flip Output Direction checkbox, the material output direction can be flipped. The visualization of the tape output will change accordingly. With the Flip Facing checkbox, the material facing direction can be flipped. This is indicated as an arrow on the visualized tape. The facing, and thus the direction of the arrow, should be set to be pointing away from the inside of the mandrel. This setting is used to determine the tool orientation during production computation. By clicking the checkbox, the visualized arrow will change direction accordingly. The Use Output Position as TCP checkbox can be ticked to define the TCP at the specified material output position. If the checkbox is not checked, the TCP is defined at the center of the roller. This set TCP location should be consistent with the TCP location used for defining the zero position of the machine in the General tab. Now we can move on to defining the tool geometries in the Tool tab. In the Payout section, we can upload an STL of the tool in the Pretty Geometry field. This is the file which will be used for simulation and collision detection. Usually, pretty geometries have a lot of details which can make the collision detection slow. Therefore, we have an option to load a simplified collision geometry in the specified field. If a collision geometry is loaded, it will be used for the collision detection instead of the pretty geometry. The tool parameters can be set in a similar way as the machine parameters. For this tool, I will set a scraping force parameter, which could be used for a wet winding machine to determine the amount of resin on the fiber. We will set the default value of the parameter to 60 and set the parameter to be non-constant. Now we can move to the Post-Processor tab. In here, you can define your own post-processor specifically for your machine. At the top of the panel, we can choose to include the actual offset in the positions. If this checkbox is checked, the actual offset set in the mandrel settings panel of the production tab is included into the machine positions written to the production file. In the file section, we can add, remove and parse files. We can add a new file on the product level, which will create one file for the entire product. If we would choose the layer level, a file would be generated for every layer in the product, while a file on the path level would be generated for every path in the product. If we select a file on the product layer, we can give it a name with an extension for a machine, like a .sjf file for a CNC machine. In the code panel, we can now write the machine file syntax or the machine's post-processor. The text as specified in this panel will be written to the files. Any meta commands used in here will be evaluated at the write time to be converted to the final text which is written to the file. The post-processor will therefore consist of hard-coded code required for your machine and meta commands to set the computed product-specific trajectories. TaniqWind Pro allows for the use of meta commands, which are certain variables, formatting settings, equations, and repetition tags. The list of allowed meta commands and their definition is specified in the software manual, which can be found under the Help button in the Home tab of the software. If we open a post-processor in a text editor where the meta commands are highlighted, we can see how the variables and formatting settings, which are both shown in green, and repetition tags shown in blue, are combined with the hard-coded machine code in white. If we now take this post-processor and paste it in the code panel, we can parse the file to check whether there are no mistakes in the use of the meta commands. This is the end of the TaniqWind Pro CNC machine definition demonstration video, where I have demonstrated how you can define your own CNC winding system in TaniqWind Pro. If you're interested in other highlighted feature videos, these can be found at the TANIQ YouTube channel.